Hey guys, so I've been working on a pretty big project for my senior year of college, and I wanted to talk to you about the project, some data structures that I use, specifically quad trees, and how they optimize really expensive code. I'm currently working on a particle-based physics engine. This will allow you to place in particles with custom properties and visualize essentially how they all conform to one another. There are two things that I have to account for. One is I have to check for collisions, and two, I have to see how many objects are pulled by one another using gravitational force. Both of these operations would normally require for each particle to check for all other particles to see if they are colliding and what the force of gravity is being applied to that particle. These are both O of n squared and can be quite expensive if done this way, making the code execute very slowly the more particles you have. If you have 1,000 particles, you are doing 2 million checks with both of those algorithms combined. That's a lot of checks, especially since these are happening every frame in the application. So how do we fix this problem? Easy. We use quad trees. So what is a quad tree? They're very similar to binary trees if you're familiar with the data type. Let me put it this way. Say your screen is the first node of the tree, or in other terms, the root node of the tree, and you enter in n amount of particles. Let's denote this variable n as 4. Once you have 4 particles in the node and you add in a 5th particle, there's no more room within that node. Therefore, we have to subdivide it into quadrants, hence the name quad tree. These quadrants are listed as northeast, northwest, southeast, and southwest. This recursively happens the more particles you have in each region. Well, now we need to understand how the collisions work. First, we iterate through each particle. Then we search the tree. We check each individual segment, check if it's subdivided, and then we check if the boundary contains the point. If it contains the point, then it most likely collides with the particles within and below in the branch. That is, the branches that it collides with. This then changes the computation from O of n squared to O of n log n, since we iterate through the array once and then logarithmically search the tree. This turns 1 million checks into 3,000. That's an insane improvement in computation. A similar algorithm is applied to objects in space that gravitationally pull each other. Instead of checking for collisions, however, you iterate through the tree and determine chunks of the tree rather than individual particles. This is what's known as the Barnes-Hutt algorithm. When a particle is placed into a node, that tree immediately subdivides into 4 quadrants, and that leaf node is then placed into an empty child slot. This means that there will only be leaf nodes in this tree, and any regular node will contain all the data necessary for the force application. What this means for traversal is when you add in all of the particles, data is stored and updated into each parent node, such as the total mass and the total force. When you iterate through the particles, you first search for the distance between your particle and the node. If the node's distance is less than a value, let's say theta, then we calculate the force of its children, or the leaf node itself if that's what we're already checking. If the node's distance is greater than theta, then the nodes are far enough away to not be a huge impact, and is therefore treated as a massive particle, and reacts appropriately. What this does is that it takes one particle and a group of, let's say, 10 particles from across the window, and it compares the mass of the general center of mass of that group of particles rather than each individual particle reacting on each other. This also computes down to 3,000 checks, just like the previous one. As you can see, we went from 2 million checks per frame all the way down to 6,000. That's a save of 99.7% in computation speed. I'm currently working on another video that will explain a lot of this in more detail, as well as the entire project as a whole. But this video was more of a quick upload to demonstrate the concept of a quad tree. These algorithms were also explained in a very shallow tone, and more depth to everything will be explained in the future upload. Anyways, I hope you guys learned something and enjoy what you had to see. If you'd like to access this project, it's currently only runnable in Visual Studio, but I will still leave the GitHub repository in the description below if you'd like to check it out. Thanks for watching, y'all have a good day.